Okay, welcome everybody. Thank you very much for joining my talk. It's my first talk on the EclipseCon ever. So if you don't like my talk, it's okay to throw stones or something like that. But always be aware I'm black and scary guy, so maybe I throw them back. I'm happy that you're all here, even if it's the last turn for the first day. And I hope you enjoy my talk a little bit. So who is that guy who's talking to you and stealing your time? My name is Olaf. I'm with itemis in Hamburg. I work there as we have this funny word, full-stack software craftsman, which just means I'm making web development, and it costs more than if other people do it. And I'm the head of the web engineering department we just founded in Hamburg. And I would like to give you a little overview. I just have like, oh, now I start the timer, so now I have half an hour. To give a little overview about my personal opinion, how it came to Reactive Streams. Because I had the discussion with some colleagues, how the concepts of concurrency and parallelism evolved in Java over time. And so, yeah. We will look into the concepts, into the old concepts and the new concepts, and I try to explain how it came to that. Okay, so the agenda. We will look a little bit into Java 1.0. It's 21 years ago, so even I feel pretty old, and most probably I'm the youngest in the room. Then we will look into Java 1.5, because there are some advanced concepts came up. In Java 1.6, I will actually use these concepts because they just made some imports for 1.5 and so on. Then we will look into the fork join framework that came up with Java 1.7 because there's a new idea started actually. Then we will look into 1.8, not really into parallel streams. They're also involved in what I'm talking about, but we will look into completable future. And then I will tell you a little bit about the flow interfaces. Okay, let's start. Once upon a time, when I was young, people used to use threads. So I have here a very little example about how to use threads. So I have an incrementer runnable that is the smallest thing I could think about that runs and increments his state, okay? So, and if I run this test, who can tell me the outcome? It will not work. So who can spot the problem? It's a little bit small, right? There are actually two problems, even if it's that small. If we start the threads and we directly look into the outcome, most probably not all threads will have run. So, right? So maybe I have to add something like make it easy. So okay, so and still if we run that, and many times it will work, but in sometimes not, because we even have to synchronize this method because it changes a state. So what will then happen is we have there these threads, and they will all have to put them into a line, into a strict line. None of them can work in parallel, actually. So maybe that's a bad example. And what we see here even, I made another example. I apologize for the resolution. I thought it would be a little bit, but maybe we use this. What I did here is I used this parallel example that we just saw, and I put an increment and serial a sequential version to it, okay? And if we run them, the outcome is that the sequential service is actually much faster. Why is that? If we look here on, this is actually the states a thread can take, okay? So if what we see here is that a thread gets created. This is quite expensive. And then it runs and runs and runs and does some things like rating and being blocked and so on. But then it gets terminated, which actually means that if we give a thread a task, and the task is ended, the thread dies, which means that all the resources that we invested to create a thread, they're gone. And maybe not even for quite a high purpose. So what came up, it's pretty easy to do a mistake, even with something very small. And it's very expensive. The other thing is that we saw, if we have the keyword synchronized, which was already in Java 1, if we have here something that we want to protect from changes from the outside, these two methods, which have the keyword synchronized, they are actually mutually exclusive from each other. What we want, right? So, but let's say we have something that has more than one field, like 3, then all these 6 methods here are mutually exclusive to each other, which means it will slow down our application. If you want to write code that will guarantee you that you just set and get from each of these states is mutually exclusive, it already gets quite not good looking. It's easy to make a mistake and so on. So okay, we came up to the situation that we need some additional tools. Okay, we don't want to be that near to what actually happens in there. We want a better concept. So in Java 1.5, and as I told you, 1.6, what I'm using just because there were some implementations. What came up were the executor pools. So what I have here, I have the same example as before, but I'm using an executor pool to execute the task. And one thing more, we have here that every step has to do something complex, which I actually added there was just checking for integers if they are primes. I just need something complex. So, okay, and if we run that, I can show it to you, but maybe it's not really that interesting to you, is that we had something very small and we already had a positive outcome about making it in parallel. Takes like 10 seconds and then we will see up to 5 times faster. Something very easy, something very small. Yeah, up to 5 times, 4 or 5 times. So there we came up with some tools, but we still had the situation, oh, we have to synchronize things and so on. So then we had the executor pools, which actually work, just to remind you how it works. You have a queue with tasks that come in, okay? By the way, I'm not a graphic guy, I'm more an software engineer, the guy who hacks in the back of the corner. So if you don't like my slides, neither do I. What we have here is we have a queue where the tasks come in, and we have some threads that we create one, and we reuse them, which actually means that we have the cost for creating thread just once, which is pretty good. So we can see it as a constant cost, and then we can reuse them. So it's pretty easy to have a positive outcome of using parallelism, which is great. So, and then in Java 1.7, and that was really important, what came up there, was the fork join framework. Who has heard about the fork join framework? Oh, good. Maybe I go over it. No. Actually, they extended the idea about executor pools with every thread has its own additional queue where it pushes in tasks, and the other one can steal from them. So there are multiple queues of tasks, which is not the really important part. The really important part is what we will see here in a little example is oh, sorry, it's not down here somewhere, most probably. Yeah, there. Oh my God, the resolution is. Should I maybe? Does it help if I decrease the font? Oh, okay. So what I created here is merge sort. Who remembers merge sort? It's a very academic thing about how to sort something. And the good thing about merge sort is that it's a really good example for fork join pools. So for those who don't remember, because I haven't seen if every arm was up, you just divide a set that has some order into pieces which are the size of 1, which are ordered then, because for sure a set of 1 pieces are ordered, and then you just merge them together. Okay? So and what we have here is we have here these tasks, And every task creates 2 subtasks, and he forks them. And that's interesting, because there we don't say which executor pool should be used. We don't say something like when should it run or something. We came to the situation that we said we think about the what, not the how. That was quite interesting at the time. And actually the pool that is used there, it's called the fork join common pool. It's used in many, many other places where you wouldn't expect it, or at least I didn't expect it when I looked at it the first time. For example, to come to Java 9, the completable future. Who has heard about the completable future? Less arms, yay! In my last project, we used parsec, for example, which is an idea from Twitter, to do, actually asynchronous composition of an element, or of one thing, okay? Because you have this situation that you get a request into your system, and then you say, okay, I have a greeting service, which is the easiest thing I can think about, and it needs the first name, which it takes from a database. It wants to have a last name, which it takes from another service, or requests from another service. And then it calculates the title, which should be used for the greeting, and then it responds with the greeting. And if we do it like this, it looks a little much like parallel, but actually it looks like this, which is not nice because, for example, requesting a database, requesting another service, that is not something we can change with our calculation power. And actually, it's quite easy with completable future to do it like this, which means I define how I combine my result, and then it runs sometime. And then I get my result sometime. Most probably, or in most situations, I can work there log-free when I work with that. Most things I do there. And again, I think more about how, what I want to do, not how I want to do it, which we see there. Unbelievable. I'm sorry, but we will make it work. What we see here is that we say supply async, which means get me that from that function sometime. It uses the fork join common pool there, which is a good thing if you have something that needs computation power. It's a very bad thing if you need something where you have a synchronous call to something where you cannot do anything with computation power, like a database and so on. So be aware if you use that you always use another executor pool there. Okay, I'm pretty fast. Does anyone want me to slow down? So you're faster with beer then. That was interesting, and then we came to Java 9, which is most probably the only thing you're here for. Is hi. In Java 9, the people from the JDK decided to put into Java 9 the reactive streams, or the concept of reactive streams, actually the interfaces. Why do we have reactive streams? As you see here, if you have a completable future, it's pretty good for doing something asynchronous, but it's not made for more than one element. Yeah, also a set is one element, but it's not made for an infinite stream. Okay? If we use streams, you shouldn't block them because also parallel streams, they use the fork join common pool. And so the concept of reactive streams actually allows you to asynchronously computate results or intermediate results for a potentially infinite stream. Okay? So what are reactive streams? It's a contract for asynchronous stream processing with non-blocking back pressure. So many buzzwords. I will explain them all. The cool thing about this is that it's created with many companies, many organizations. It's a pretty easy contract, and multiple libraries depend on it. So that's pretty cool, actually. There are multiple implementations. They play our song. There are multiple implementations, for example, Akka streams in Scala. Reactor, who has used Reactor before? I like it a lot. It's now into the newest thing that Spring came up with. It's integrated, pretty cool. Who has used AXJava before? No, also quite nice. MongoDB Reactive Java driver, never used it, but people told me it's nice. And there are others, and they are upcoming. And not just in Java, and not just in JVM languages. For example, for Swift, the interface is defined and so on. This is how actually the interface looks like. The interfaces. You see here 4 interfaces: a processor, a publisher, a subscriber, and a subscription. Don't be scared of a processor, it's just a publisher and a subscriber together. Okay? So, what is the idea of Reactive Streams? The idea is you have a publisher that publishes something, a subscriber that consumes something, and if you want to have a producer in between, you put them in a line. Okay. And it works pretty easy. So a subscriber subscribes to a publisher and tells him that he wants to listen to results of the publisher. And now we come to the situation with asynchronous and backpressure. The publisher doesn't publish anything to the subscriber until the subscriber requests something. And he even requests the amount of items he wants to consume. Backpressure means that, or the concepts of backpressure, there are multiple implementations, but the whole idea is that the publisher doesn't depend on the subscriber and vice versa. So it's not possible that you overproduce, which you sometimes have. Imagine you have a sensor that gives you like the temperature 1,000 times in a second, and you have there a very old database running on a, what was it called when you were young? These things with the, you know, this really old data storage. So you cannot even write them all down. So you can only write down what you can consume. So you actually just get what you consume. That sounds pretty easy, but yeah, just to go back, the demand is null, so you don't get anything. There are many strategies like actually telling one is, and that doesn't really work to the contract. One is to actually stop the publisher, which is not mostly not the idea, because the publisher should be able to work. And there's never the idea to give the subscriber anything he doesn't want. That is the most important thing in the contract. The publisher never sends more elements in the subscriber request. So that means you cannot, from your own application or your own system, you will not get stress tested all the time, just because you don't even want to work with that much request. Okay. What the little problem is, as you see, the library comes from org Reactive Streams, blah. And it's published there on GitHub like at least 2 years. And in Java 9, they decided to copy it. It's actually, or let's not say copy it, but it's equal. But as you see, they are not in the same path. And they even put into a class, which is not a real problem. But the thing is that now, I think for AXJava, they already did something like that to create a bridge to allow you to use your Java 9 Flow publisher implementations inside of AXJava. Because most libraries, they still, and they will, most probably, be according to this definition. Okay. So, no, we're not at the question, but we are near to the end because I was too fast. I'm sorry for that. But maybe someone of you has to tell something. I have here a little implementation just to show you how it looks like. I made it with AXJava. And what we have here is, it looks a lot like streams, right? You work in the same way. You say, I have something, and if I have a result, I do something with it, and maybe I join it, which means zip in that situation, with something from somewhere else. And then at the end, someday I have a result, and then I work with it. Okay? What is nice here is, if you actually create implementations for the publisher interface or for the subscriber or subscription or processor interface, you can reuse them. You write them for AXJava, and then you find out you don't like it anymore. which shouldn't say anything against Java, but maybe it comes up that you do your own fancy library or you want to use Reactor or whatever. They are all compatible to each other. That is actually the really nice thing about these contracts. This is a nice thing that came up with Java 9, that they add the contract, and if you have a bridge, okay, you're still fit to the contract. Okay. Yeah, like I said, I was pretty fast. I haven't expected it. Are there any questions? Yeah.
Did I get it right that in Java 9 I really only have the interfaces and I basically have to use one of the existing implementations also, like Java?
How to say, you don't have, you would create your own implementations. Yeah.
Probably quite fun.
What?
Which is probably quite fun to implement myself.
Actually, there are some examples. For example, in the org Reactive Streams, which are pretty easy versions. It gets harder if you want to have back pressure concepts and so on. You're right. So yeah, they just created the path to then add it. A little bit like what they did with Java 5 and then Java 6, where there actually came up some very cool implementations. But since the new version schema is out and Java wants to evolve faster and faster and faster, maybe there will be some cool implementations in the next version.
If you would refactor code that exists and it's usually processed in a sequential way, how fine-grained can be the operation so that it's not an overhead to do it asynchronously? For example, for sorting things, for building up trees, and so how fine-grained can the operations be?
So you mean the operations that you have to synchronize?
That they have to execute. I think it's obvious if you have some operation where you query database and get some result from some servers here, and so these are long-running operations, and they can be processed asynchronously and then joined together. But if you have some computational code like in Eclipse where you compute the change tree and process the change tree of resources, would this also be subject to refactor to do this asynchronously?
Actually, to give the consultant answer, it depends. The thing is, I would expect if you very short running operations, but many of them, then I would actually measure if they are enough that it would be better to run them in parallel than to have or that the cost for instantiation and pool for it. You know, you have the cost for instantiation and pool, but then you can do like whatever 16 or something like that of them in parallel in best case. So you actually have to measure it. Like with most things you do with parallel things, you have to measure it. I would try it out if you really have a lot of them. But you have a little bit of overhead if you always create a task for them. Like I said, maybe measure it. It should be pretty easy with executor pools and so on to change it. Most probably it's just 3 lines of code and then you can measure it.
Now that you said you can run 16 of them in parallel, is there any best practice or recommendation on how large thread pools should be?
I for myself use the amount of, I have an Intel CPU, so therefore I use the CPUs multiplied by 2 because of the, what is it called? Yeah, the hyperthreading. Most of the platforms I publish my services on are based on Intel CPUs, which has the same architecture. Yeah, I do it like this. But for sure, smart people have thought about that, but I don't read the long papers.
The common thread pool is
the common thread pool, yeah, right? Yeah, I think he uses the number of processors, not the number of processors multiplied by 2.
To enable that threading.
Yes. Yeah. So their smart people thought about it. Okay.
So you're a web developer. Obviously, you're programming in JavaScript as well. For you, what is more natural to you to program? Is it the reactive streams, as they are now, or the concept of fork join and thread pool known to you as a JavaScript developer?
These concepts are not from my point of view, these concepts are not for the same problems, from my personal point of view. Like with everything, it depends. If you have what you have mostly in microservice systems, I building, is you have many requests coming in, and so you want to process them and then produce an outcome. And then reactive streams is something that feels very natural. Maybe even in some situations, if you just have one result, to combine them a little bit with completable futures, which we actually do in some situations. Because that's why we used parsec in the first place, and then we dropped it for completable future, not because it was bad, but because it was part of the language, and for us it worked in the same way. So it's not that from my point of view, you shouldn't replace everything now with doing it with reactive streams instead of executor pools or whatever. I wouldn't do that because like I said, it's pretty easy to shoot yourself in the feet with it because you have the common pool behind it, and the common pool is not made for requesting something where you don't have the computation. So if you don't control the computation power, it's pretty easy to block your whole common pool just with requesting databases coming from like 16 requests. Then you can even block your executor pool if you do it wrong. So don't do it. Use separate executor pools for separate resources. And yeah, so it's more like another way of using them. Still be aware of there are many executor pools. With Hystrix, for example, you do things like that, using different executor pools for different resources and so on. Something also to look into, but it's another purpose actually what they do.
When you explain the fork join approach, you use the example of merge sort, which is the very natural example for this, because actually forks and merges afterwards. Do you see another class of applications or problems we would also use or recommend the fork join tool?
Just things where you need computation power, like I said. That's pretty important. And so therefore, everything where you actually think about something where you traverse a graph, for example, to search for something. Because you can break down every graph down to a binary tree, right? So, or every duck down to a binary tree. And that's what I, for example, use it for a lot.
You would not use it for something that does not actually split on space.
You can do that, but then you don't have all the upsides of having these. I'm not that fast with the presenter. I'm sorry. You don't have all the upsides with the other queues and so on. So you have the downsides of using the resources, having their threads, checking if in these queues there are some tasks or whatever. Yeah.
Maybe I missed it, but we pointed out multiple times that we shouldn't use fork join and stuff like that for non-computation operations. But the example of asking two microservices in behind for the first name, last name, and combining the result is exactly that, because I'm just waiting.
You're absolutely right. That's a good thing where you can in computable future, you can explicitly, if you don't set it, it uses a fork join pool. But if you set it, it uses the executor service that you give it. So you create an executor service, for example, for every task that goes against the first name service. And then you're sure that they are in a line, they just use as much threads as you defined and so on.
Yeah, and that's obvious. And how do you then decide on the executor pool sizes? Because then each developer who works on the microservice introduces a new pool because it calls new backends, and then it grows uncontrolled.
There's a good question. Actually, that goes a little bit into how should a microservice architecture looks like. Because if you have like 20 dependencies, then it's pretty easy to break your service. Because, you know, if you want to be resilient, you have to cover your ass against cover yourself against every dependency you have, so it cannot break you. If you have something like that is that complex, I can only tell you to look into Hystrix that has good concepts for that, and that helps you a lot about that. But there's no, Okay, it seems like we have like 4 minutes left, so if you don't want to ask me more, I hope you enjoy the beer outside. Thank you very much.
Thank you.